right, so I think we can get started. I'm recording now. Everyone can hear me? Yes?
Да-да.
Okay, so I just want to welcome everyone to the June 2020 Thug, which is the first of its kind because it's online. And also, we're having a little bit something extra special. We're gonna have also live translation as well. Which is also a little bit different format because normally we hosting Thug at the side effects office, and probably in a few minutes Anatoly would be talking in the dark to a room full of people. But that's not happening because, well, we all know. So I thought instead, actually, I would take this opportunity to have international guests and different time zones so that we can kind of somehow take advantage of this opportunity to have Alexei join us, which he would not otherwise be able to if we were having like the traditional Thug format in person. So if this kind of explodes and like doesn't work, then well, hey, it's like fun experiment, I think. So I want to welcome Anatoly and Alexei to this Thug. If you guys want to say hello.
Hello, it's
Привет.
Anatoly.
So Anatoly is going to help to translate some of the answers, or actually, hopefully, all the answers from Alexei. So this is just a little intro before we get into Anatoly's presentation. I just wanted to have Alexei join us because for the past couple Houdini releases, we've seen this plugin, this modeler tool that's been coming like on forums, and people are talking about it, and I thought it would be cool to have the developer of that tell us about this tool, tell us about where it came from, like what's the idea, how did you actually, Alexei, come to start like making this tool? What inspired you? What got you started to make this tool?
Ну, я начал заниматься графикой с 9 лет.
I started doing graphics from when I was 9 years old.
Я начал на простых, игровых компьютерах. И тогда я уже на бейсике, мне нравилось писать компьютерную графику.
I
Потом
started.
с 99-го года я установил Майю, и тогда началось 13 лет жесткого программирования в Майе.
So I started.
Wait.
Подожди секунду, я переведу сейчас.
Да-да.
I started with the basic, the simplest computers, programming in BASIC, and in 1999 installed Maya for the first time, and then there was the period of hardcore Maya programming for 13 years.
Oh shit. Okay.
Да, и потом в 2013 я уже психанул и установил Houdini и сказал, все, буду моделирование тут писать, потому что в Мае свои проблем куча, плюс автостол, все дела. И вот на форуме, когда я выкладывал в 2015 году информацию о своем моделере, воспринималось это что скептически. Говорили, что в Houdini никогда вы не сможете моделировать как 3D Max или, например, Moto.
Секунду, переведу.
Ага.
So in 2013, I rage quitted Maya because of all its problems and Autodesk issues, and just installed Houdini and started developing the tools. And
На самом деле я ставил еще в конце 2000, но я окончательно на Houdini перешел в 2013 году и просто удалил Маю. И завязался с теми своими клиентами с Майей.
So
Все, что не связано с Майей, вообще с миром Майи.
So I actually was looking at Houdini since 2000, but in 2013 I actually just deleted Maya, quit all, closed all connections with the Maya-related clients, and switched to Houdini completely. So in 2015, when I first published my modeling tools on forums, I got really skeptic responses, like saying you will never be able to do modeling like in Maya or Max in Houdini and stuff like that.
And Maya was the single source of inspiration for developing these tools, because when you're making the tool, like it kind of somehow feels a little bit like sprinkle of Modo
Да, да.
or other applications. So how are you able to develop these tools? Like, are you working with other artists to get feedback from them, or you're coming up with these ideas and tool logic yourself?
Нужен
Ну,
перевод?
Майя была как бэкэнд, и на самом деле программа, которую я поднесу, не так уж и важна. Я всегда в курсе, что последнее в Максе, в Модо, в Сило, в Блендере, и все это, ну, я всегда в курсе. Инструменты я постоянно анализирую, и хочется сделать так, чтобы художникам не пришлось тыкать, нажимать мышкой по 1000 раз. Вот это главная идея модельера.
Maya was the backend, but I'm always up to date with everything new in all the software. Maya, Blender, Modo, whatever. I forgot other software. Yes. Yes, and the point is to make it uniform experience.
Код и ZBrush по-любому тоже туда же.
3D code and ZBrush as well.
Yeah.
But just to make a artist-friendly experience without having them switch between softwares.
And this last update that you did for the 2020.1, how long were you working on this update? Those features look really impressive in the videos, like especially the kit bash and inserting mesh and the little library area where you can just drag and drop.
Там на самом деле в видео показано далеко не все, и разработка она плавающая, как роллинг релиз. Я могу релиз выпускать 1 год, например, могу полгода.
So
я могу год сидеть ночью и днем, так, без перерыва.
Okay.
А потом делаю релиз.
So there was the thing you saw in the video is not everything that is actually there. That's rolling releases, so can be developing it for the whole year or like night and day developing the stuff.
Yeah, I was going to ask actually if you're spending full time on developing this.
Yeah.
Other jobs.
Full time.
Yeah,
Full time.
Okay, yeah. Well, I mean, it's not small work, like we can all see. So, like it's good to hear that you're fully focused on that, and people can expect that they have.
Ну и в текущей версии, сейчас что у меня на компьютере стоит, там тоже очень много нового. Воксельное моделирование, экспорт ZBrush, прям, в один клик, можно сказать.
So the version in development has much more new features like voxel modeling and one-click ZBrush sync expert.
Like a live sync?
Live link. Between ZBrush. Without лишнее телодвижение.
Without any additional effort. One-click link.
Без такого понятия, как файл.
No intermittent file.
Я не знаю, что такое файл.
Say again?
No intermittent files involved. Just one-click link. Everything live. No files. No experts.
I don't know what to say. This is like very impressive. So thank you, Alexei, for sharing with us this probably small piece of what is involved in the daily working of maintaining this tool. Do you have any wishes actually for Houdini, like future features?
Конечно. Миллион.
Finally? What? A million?
Million requests.
Вы знаете, как работает мода? Там есть слаженная сетка OpenSubD. Вот это самое главное. Больше ничего не надо.
Way Modo works with the OpenSubD, the smooth mesh. I don't know. I don't use Modo, so I'm just translating.
You're talking about the performance as well, right?
Cosmon Clark Subdiv прямо на
Yeah,
модель.
yeah,
Just
yeah. I know
like
what you mean. Yeah.
это самое главное для дизайнера. Плюс скульптинг, ускорение, как бы в Houdini постоянно все кукается. А надо, чтобы были какие-то локальные места для редактирования геометрии. Вот это самое главное.
So Houdini always cooks everything.
Скульптинг. И лучше даже, чем ZBrush. Ну, на данный момент постоянно все кукается. Если я отправляю геометрию в 6 миллионов полигонов, в Houdini тяжело это переварить.
Houdini always cooks the whole graph, and that makes making sculpting tools hard, because you would want everything kind of to be localized, the geometry, the modifications in some one node. So that is the problem.
Но на самом деле мне очень нравится, как работают разработчики и пишут узлы внутри. Потому что контекст, это там на самом деле талантливые люди пишут. И мне просто нравится этим пользоваться.
But I very much appreciate the standard tools, and I very much appreciate how developers inside of it make them. It's just nice to see.
Okay. If they don't listen to this already, I'll pass the word on to them.
I have a question actually.
Yeah.
For side effects part. Like, are you guys being inspired by Alexei's tools, and are you stealing something maybe for future releases?
I mean, I'm not head of R&D, so I feel like I'm not the correct person to reply, but I will say no. But certainly we do pay attention to not only your plugin, but all software development across the board. We like to see what others put out and try to, let's say, stay current. Obviously, there's also, let's say, maybe I'm saying this wrong, but architectural limitations or some other limitations in place that kind of prevent some specific workflow to be implemented, as far as I understand. But I'm not a developer, so don't hold this to me 100%.
Нужен перевод? Отлично.
Я понимаю, я визуально, на слух я все понимаю. Все, спасибо вам.
Thank you.
Cool. Thank you for joining us. And now, Tolia, let's talk about you. How did you get into 3D? Did you start in 90s with Maya,
Oh no.
Alexei, or you're a Lightwave guy, or 3ds Max?
Well, depends on what you mean by started. I guess first 3D program that I saw was 3ds Max.
Which version?
5, I think. But it's I saw it on the screen and I created a cube or something. And whoa, this is way too complicated.
And then you ended up doing that a couple of years later, how to animate a cube. Is that a homage?
That was a bit of a joke. But the point is that I never took it seriously. I was studying at the time in university for a computer science degree. So I had a hobby of just animating actually something in 3ds Max. And with a long and very weird series of events, I ended up...
That sounds like Lemony Snicket.
Yes, it was really, really weird. I don't know if I should dive into that.
Please.
Well, just as I was finishing my degree, I was contacted by a guy who saw one of my animations and wanted to make a full-length feature movie. Yes, and obviously, being young and naive, I thought, damn, this is good. So I actually dropped out of the PhD program to do this, and you can imagine that it didn't go anywhere. So, I mean, after 2 years of work, and
my God,
I had no experience. There was a team of experienced people, but very small team, as I now understand. Very small team, very under-budgeted team, and after 2 years, the investors' money ran out, and I kind of realized that now I'm in a position that I don't have money, I don't have work, I didn't finish my PhD, So, and I need to pay rent since I already lived in Moscow. So, and luckily now I had some friends in the CG industry with with whom I was working those couple of years. There are actually even the cringy trailer available from what we did that, but I hope no one will ever find it.
I think we are totally gonna play that as we are talking about the story now.
No.
Come on.
Well,
it's like a time capsule.
Yeah, I don't want to see that.
Okay.
But yeah,
now
it's
everyone will go to search for it.
Okay, and basically, like a couple of months before it all ended, one of the guys showed me Softimage, and I loved it. I loved Ice. I haven't heard about Houdini at that point. I think I saw it once on one screen and thought, oh damn, that's complicated stuff. So yeah, I went with Softimage. It was very nice, and the Ice, yes, Ice was great, and I managed in a couple of weeks to learn Softimage just by myself and get a job. Well, with help of a friend as a fixed artist for some TV series, and yeah, that's how I got into CG basically. And then
I didn't know that you were a softie.
What? A softie?
Yeah.
Yes, I stuck with Softimage I think up till 2015. I switched to Houdini 2015, I think. Yeah, it was so sad because I saw that Softimage is dying since Autodesk bought it.
Yeah.
It just got no improvements whatsoever. It was sad times. Yeah, and I always thought that damn, Houdini has a similar thing, the VOPs. Well, I was just taking a look at it and never did anything there. But the VOP context is just so, compared to Ice, it was just nothing. Ice was so much better. Just because the paradigm was different. In Ice, there were things to mix context, the tools to mix context. There was the whole different approach to this. It just looked similar. So yeah, I was always like, Houdini, what can it do? The VOPs are nothing. Yeah, but then when I actually got into it, since I understood that there will be not much jobs with Softimage anymore, I grew to like it more and more, because yeah, they actually turned out to have way more possibilities than Softimage.
And you were doing that in your own time?
I mean, switching from Softimage.
Yeah, like you were still working somewhere, or?
Yeah, that was a weird time, I must say, because no one cared how I made something, as long as I make something. So I actually switched it at work. I think I was the only one working on Softimage at work anyway.
Okay, wow. So like fast forward to today, like what are you doing these days?
Oh, same thing.
No, like you moved to Toronto, and like tell us like where you're working, what you do.
Well, currently I'm working at Mr. X. I think the official position I got into here was the senior FX TD, but I think the TD part and senior and the FX actually is up to interpretation, the studio by studio. Some studios call everyone TDs, some studios call everyone artists. So
yeah, that's kind of like a blanket title to cover a lot of things. So then what exactly do you mostly do?
I do tools. I make tools for artists, and I make the fixed side of Houdini pipeline, and sometimes shots as well.
So you do everything?
Yeah. The support as well.
Like
when people need help.
Emotional support?
Hug them when they need it. Even deadlines.
By the way, I totally forgot to introduce you as Harkonnen, because that's how I was actually going to start that, but everyone, I think, like, nobody probably knows your name, but like they all know Harkonnen, or like the English pronunciation of it, which I'm not even gonna try.
I would try. I think it's Zapkocha.
I mean, like, everyone should read Cyrillic anyway, so.
Yeah, it's the future.
Yeah. So people know you with that handle and also the how to animate cube. Like, can you tell us a bit about like what is the Harkonnen name for you and also the cube thing? Is it really the homage to like Max?
No. I mean, about the name, it just got stuck with me since I played Counter-Strike in computer clubs in like early 2000s. And then I registered the mail on Gmail, and I think Gmail was
free.
just well, it's still free.
No, I mean like the name was free.
Oh yeah, I first heard about the Gmail and just registered it.
Yeah, I remember that time too.
And I got stuck with it. I never thought it would go any public, so just whatever. Name is a name. Yeah, now it's a bit unpronounceable for English audience.
And the animate cube, I mean, that's like super cute overkill.
That was very spontaneous video. I think I made it in a week, just after a deadline to get my mind off something. I mean, mind off the deadline.
Yeah.
I just got an idea during the deadline that can you do actual physics with Houdini, doing the smoke solver feedback and do some geometry. And yeah, I tried it. The engine worked, so I thought, oh, just step forward, just put the engine on the car. And then I thought, I should make it a video, maybe a funny one, so I will subvert expectations. It was just the first thing that sprung into my mind. Just make it like cube animation. So there was no idea behind this, no deep thought about it. It's just a video I made in a week and put it online for fun.
So what is your presentation going to be about?
It's going to be about similar things, with a fancy example of not cubes this time. Hello, my name is Anatoly, but I'm probably more known by my nickname on Vimeo, Zepkoch, or pronounced correctly, Harkonnen, or just that cube guy, but it's getting dated. That video is what now, 3-4 years old? So let's distanciate ourselves from the cubes. Today we will talk about something completely different. So different, it's basically the opposite of the cube, maybe even cube's natural enemy, the sphere. And we will pump those spheres with hot air, give them little cute personalities, and then give them railguns to kill each other. Just like this. This may seem as one complicated simulation, but actually it's composed of a number of smaller and easily even more complicated parts. That was a joke. Those smaller parts are probably less or equally complicated. I will explain logic and algorithms used in this simulation without going too much into coding details. Details you will be able to see for yourself. But sometimes old enemies have to team up to oppose even bigger threat. Presenting Balloon Fight 2. Balloon Cooperate. By the way, interesting thing I noticed talking to different artists and TDs, DOP is generally the least understood context. Of course now SideFX tries to top it with LOPs, but I think DOP will keep its first place. So what are the subtasks we need to solve? We need to figure out how to do Pyro to Vellum and back stable mutual interaction. We need to figure out how to dynamically rip Vellum balloons. And we need to figure out how to make balloons do smart things. We start with Vellum to Pyro collisions. It's important to understand the basic concepts of DOP context. This is way out of scope of this presentation, but in short, DOP nodes are not objects, but they are tied to each other. Top node network describes the way to create and modify objects. There can be more than one object created and processed by one node. And objects are the ones that actually do the simulation work. In case of vellum to smoke collisions, the base of our network will look something like this, where left and right branches produce vellum and smoke objects respectively. In actual battle scene, however, there will be one vellum object with all balloons in its geometry data, but multiple smoke objects, one per balloon, produced by the same smoke object node branch. So, vellum and pyra are different DOP objects with different solvers. DOP objects' interactions are defined by relationships. By interactions here, I mean anything, not just collisions. In its core, it's just dependency relationship with some data attached to it. Relationships have affectors and affected objects. Therefore, as long as those lists of objects do not intersect, relationships define the solve order of objects participating in them. Like in this example, object K needs to be solved before object Yo to respect the relationship. As a note, we will be talking now only about case when colliding objects have different instances of solvers attached to them. In case of same solver instances, all objects will be passed to the solver at the same time, and collision handling will be left to the solver itself. Multiple relationships may exist. Final solve order will be deduced from them. But sometimes there is multiple valid solve orders. In such cases, independent objects will be solved simply by their object ID order. So we have a collision relationship between our vellum and smoke object. The default way to create such collision relationship, everybody knows intuitively, is to plug objects node graphs into a merge node that by default is set to create left to right collision relationship, meaning object A, vellum in this case, should be collider for object B, smoke in this case, but B is nothing to object A. Therefore, first object A must be solved, then object B. And it's up to specific solver to treat the collision part of the collision relationship. So far, easy. But how to deal with mutual relationships? Because this is exactly the kind of interaction we will need between our vellum and smoke objects. That max feedback loop parameter on DOP networks that most people never touch should give us a hint here. Now, the following information is deduced from theories and experiments, because I couldn't find any clear description of that process in any reference material. So here it goes. When two or more objects are in a mutual collision relationship, they get still solved in the same definitive order. As in one-sided relationship, here object A, vellum, is solved first. Then object B, smoke, is solved using A as collider. But then solver B on object B may add some feedback data back onto object A. If such data was created, Houdini will see that. Houdini will see that and consider starting a new feedback loop iteration. If a new feedback loop iteration is started, all objects will be restored to their state before solve, but keeping that feedback data. Now again, just like the first time, objects will be solved in the same order, but this time when solving object A, it has a chance to look at that feedback data it now has and adjust its behavior accordingly. But it's totally up for object A's solver. It might not look for feedback at all, making all these solve loop iterations useless. In our case, one vellum and multiple smoke objects will be participating in one feedback loop. In general case, each iteration the object being solved will use objects already solved as colliders and may add feedback data onto them. But in our case, multiple smoke objects will use vellum as collider but not interact with each other at all. So each smoke object will use vellum as collider and will add some feedbacks back onto vellum object. When does the loop stop? Feedback loop will end if no more feedbacks were created during the last loop iteration, or obviously when that max feedback loops parameter was reached. Default value of 2 means there will be maximum of 2 loop iterations in total, including the first solving of A and B without any feedbacks. This is the mechanism we will take advantage of to make Vellum collide with smoke in two-sided way. Now that we figure out the mechanism, 2 questions left. How to make smoke see Vellum as collider? What is feedback data? And how Smoke Solver creates it? And how can Vellum react to it? Smoke Solver uses build collision mask node that looks for SDF representation for the collision object's geometries. By default, it will look at geometry data on Vellum object, looking for SDF representation subdata on that geometry. If it doesn't find one, it will actually create default one, but it will be not very good or controllable at all. Therefore, we attach our own SDF representation data onto Vellum geometry. This node has similar interface, almost the same as volume collision tab for the static object. But since we're going to have potentially very sparse Vellum geometry with all the bits and pieces flying around, we cannot rely on standard SDF collider creation methods. It's just too slow and heavy for our scenario. So just like with static objects, we need to provide an SDF VDB proxy for it. We do that by attaching yet another geometry data where our VDB is gonna be to SDF representation. Now we will create that VDB in a subsolver after Vellum solver in any way we need and save it into the geometry attached to SDF representation set to volume sample mode. This way, when build collision mask node asks Vellum for collision information, it will be redirected right to that prepared VDB, which is gonna be very fast. Okay, we have a good controllable way to create collider from Vellum for the smoke. Now, how do we create that feedback data? What exactly is that feedback data? In short, it's a set of records of where and how strong of an impulse need to be applied to the object back in order for it to react to the collision. Unfortunately, Houdini provides us with a very limited set of tools to work with feedbacks. Luckily, here everything is already done for us. One of those feedback creation nodes that Smoke Solver uses is gas feedback. It creates feedback information on collider objects in collision vicinity based on how the pressure field that Solver calculates pushes onto the collider, 1 record per voxel within a certain bandwidth. Now back in Vellum object, we are adding a subsolver to use those feedbacks. Luckily again, subsolver comes with a preset import node that brings in feedbacks. Unluckily, the way that feedback data is stored and retrieved in subsolver is very slow and inefficient, being one of the bottlenecks of the whole simulation. Gas feedback node creates 1 record for each voxel within some bandwidth of the collider, and it seems that feedbacks were never designed to work with high-resolution volumes that can produce hundreds of thousands of impacts per single iteration. But anyway, it works at least, and we can import those feedbacks as points, with force being applied to the closest Vellum point. By the way, be careful here with PTNum attribute on those points, cause it shadows the built-in PTNum attribute. Now, in the subsolver with a simple wrangle over Vellum points, we find closest feedbacks and apply received impulses as force. Obviously, having several feedback loops is very expensive. Each loop iteration, every participating solver has to be solved, so 5 loop iterations makes him 5 times slower. The more feedback loop iterations there are, the better solution converges. Assuming you have stable convergent sim, of course. Therefore, we actually want to have as little iterations as possible to reach desired stable look. For my case, 3 iterations already behaved good enough, but 2 iterations produced some instabilities near high pressure smoke, causing little jittering here and there. And here's the overview of actual setup that implements all said above. You can see on Vellum part, we first apply feedbacks, then solve Vellum, then subsolver produces volume representation. Then Smoke Solver just does his thing without any modifications. Just don't forget to set the feedback scale to something greater than 0. And there we have it, good controllable two-way interactions between Vellum and Pyro. As a note, I did want to use new sparse solver for this example to be a bit more up-to-date, but it doesn't yet support OpenCL, and CPU version was just too slow compared to OpenCL version of standard solver on my crappy laptop, since our smoke is not very sparse by nature. But the sparse solver follows the exact same logic. It uses exactly the same build collision mask node and gas feedback node. Dynamic volume cutting. It's time to make our balloon stir. I will describe the logic of the algorithm without too much details and special cases as always. All that you will be able to see for yourself in the heap file. The algorithm consists of three main phases: create edge group to cut edge group to cut, duplicate and rewire constraints accordingly. Note that these three stages will not depend on each other, therefore algorithm of each stage may be changed independently. Now, in most general case, constraints can go wherever they want, and we run into problems where and how to cut them. In this picture, for example, imagine we want to cut the geometry along the orange edge. Here. What exactly do we need to do with those distance constraints marked with question marks? Sure, we can imagine something, but to prevent us from thinking, let's impose some limitations. What are those limitations? Mesh should be triangulated. This one is pretty easy to achieve, and actually we don't need it that much, it just makes things a bit easier. Second, no non-manifold points. Here I mainly mean no places where two triangles share one point on their open edges, so no dangling polygons. Next one is all distance constraints must correspond to edges, and all bend constraints must only exist between two neighbor triangles. So two triangles that share an edge. This way it's very straightforward to determine which constraints to cut when edges get cut. And actually, Vellum configure cloth node creates constraint structure that fits our limitations by default on a triangulated mesh. No extra work needed here. And actually, in some demos, I was using additional constraints not satisfying those requirements, like struts on the doll, but I was aggressively deleting them near the cuts. They were merely supporting constructs. So as long as you know what you want to do with those arbitrary constraints, that constraint limitation can be lifted easily. As you can see, a good triangulated remeshed mesh has a pretty regular structure that gives us an ability to easily determine edge loops, as you will see in just a bit. This limitation can easily be lifted by applying a more complicated and general algorithms for edge loop detection. So here we have a hit point from intersecting a weapon ray with a mesh. Here we simply detect closest point to initialize the cut group with every edge around that point. Regularity of the grid helps us here. Initial cut group can be generated just with a loop of point hedge next calls until it returns -1. Next. There is no guaranteed order of those edges, and we don't care about the order anyway. Now we will expand this group by iteratively for each edge, adding next edge in the loop. Here is where we again take advantage of the kinda regularity of the grid. To get the next edge, we just need to turn around the endpoint, skipping exactly 2 edges. And that we will do with consecutive hedge next and hedge next equiv calls. Next equiv, next. And here we ended up with the next edge in the edge loop. Same for the next edge in the initial cut group. Edge next equiv, next equiv. We skipped exactly 2 edges, and edge next gives us the next edge in the loop. Now see, as our grid is not exactly regular, places with 5 and 7 edges in one point will pop up. But we can take advantage of such cases and turn around the point in both directions, here and here, creating branching term pattern for free. And we continue this. We can repeat that expanding stage until we have big enough tear. Now that was pretty easy, and on top of that, remember, the cutting algorithm doesn't care how the edge group was produced, so we are free to change the logic however we want. Cutting the mesh is a bit more tricky. We will do the cutting by splitting each point of the cut edge. We will look first at the random point of the edge group to cut. Here the dark brown represents the cut group. We start with a random edge starting from that point. Now say if by forward rotating around the point I mean clockwise rotation, we will walk edges around that point backwards. Same way as with expanding the group, edge next equip plus edge next calls will help us do that. So we walk all the way backwards until either we make full circle or hit an open edge, like this. This is all just to ensure that when we walk forward, we will walk all edges. And if you remember, one of the topology limitations we imposed was that one point cannot be part of more than 2 open edges. So this situation is not possible. Now, stage 0 is completed. Stage 1. Circle the edges forward till we find first edge of the cut group. Or skip the stage altogether if we are starting with an open edge. I know, this stage could very well be combined with the previous backward search, but the more stages the better. Stage 10. Now that we are at the edge that belongs to the cut group, we will search forward all edges until we make the full circle up to this current edge, or hit another open edge. Each time we encounter an edge belonging to a cut group, we will replicate our current point and rewire all next edges to it. So let's watch. Next edge. Here, we encountered an edge from the cut group. So we duplicate the point around which we're rotating. Next edge source vertex is rewired to the new point. On this picture the new point is offsetted from the original, but this is just for demonstration purposes. Nothing is shifted in the actual algorithm. We continue rewiring until we reach the beginning. And the cut is done. Now let's look at a more complicated example to show that the amount and configuration of cut edges doesn't matter for this algorithm. Again, we start with the stage 1 and we look for the first edge from the cut group. Assume we already did the backward circling. Edge found, so we start the main loop. Next, as we reach another edge from the group, the point is duplicated. And the next edge source vertex is rewired to the new point. As it turns out, the next edge actually belongs to cut group as well. So after rewiring, we duplicate the original point again. Now following edges will be rewired to this new point, like this. Rewire the next edge's source vertex, and same for the last one. The cycle is done. Everything is cut exactly as it should be. Also note that we haven't changed the primitive order or the order of vertices in any primitive. For constraints, remember we had 2 limitations. Bend constraint may only exist between 2 triangles that share an edge, and distance constraints are only allowed along edges. If stretch constraint is along an edge being cut, we know exactly what to do. We need to duplicate it for both new edges. Same way, if an edge between 2 triangles is cut, we know that if there is a bend constraint between those triangles, it has to be just deleted. So we're dealing with a trivial case of constraint configuration here. But there is no natural limitation on how to deal with other cases of constraints. For example, you can introduce non-trivial distance constraints and delete them, say, by a cut surface of a certain depth created from a cut group. What helps us at this stage is that we can rely on vellum geometry and constraint geometry points to have direct correspondence between each other's point numbers. And on that, our cut algorithm doesn't change primitive number or vertex order in them. That will make matching of geometry before and after cut very easy, because we can safely remember primitives and their local vertices by the numbers before cut and find them by the same numbers after cut. So a bend constraint looks like this in the viewport. The form doesn't mean anything, it's just important that it defines the bending edge And we know that the bending edge will always correspond to an edge between two triangles. So here we remember left triangle's primitive number with vertex numbers, for example, here it's 1 and 2, and right triangle's primitive number with its vertices that in this example are 0 and 2. So we remember it on the geometry before cut. Now, for each bend constraint, we check those remembered primitives on cloth geometry after cut. If at least one pair of vertices that used to be wired to the same point is now wired to different points, easy, kill the constraint, it has been cut. For stretch or distance constraints, they either also lay on edge between two triangles or on open edges. So for each distant constraint, we remember 2 or 1 triangle it corresponds to, here it's 2, and their local vertex indices of the points the constraint connects on surface geometry before cut. So here we remember left triangle, vertices 1 and 2, right triangle, vertices 0 and 2. Those numbers are just in this example, it can be anything. That's why we need to remember them. Now, just as for bend, we find those triangles on geometry after cut and see if vertices got separated. In any case, we will rewire constraint to the points corresponding to remembered vertices of one of the triangles, in this case right, but doesn't matter. They might as well have not changed at all. For example, if those triangles had nothing to do with the cut. After that, if at least one of the vertex pairs got separated, we duplicate this distance constraint and wire the new one to the remembered vertices of the second remembered triangle, in this case left one. Now we can also reduce the constraint strength twice, since the constraint got kinda divided into two. Well, now there is one little detail about constraint wiring being a bit different from corresponding surface polygons wiring due to welds, but that's a small obvious thing, so that just skip all this, skip. And that concludes our presentation. Oh wait, I forgot to mention balloon behavior logic. Exclusively for this demonstration, I had to develop a completely new and unique device called BPU, a balloon processing unit. It was manually installed on every balloon and it behaves suspiciously close to finite state machine, but it's actually a completely new exclusive patent pending device. It has a finite set of states though, with triggers that switch them. No. Just look at the example. Only our balloon state machine is a bit simpler. We start with a chill state. Then on timeout it switches to aiming state. When it aimed good enough, switch to charge mode. It's just some time when targeting is locked and balloon is not aiming, letting physics sway its aim off and make battle longer and more exciting. Then the fire state, just one frame of firing. And back to chill. And each state can now be easily assigned a phase. The implementation is straightforward. A bunch of attributes on the balloon's base hold the current state, and a bunch of additional variables required for each state. And all the logic is just in one wrangle with a bunch of ifs. The throttle is enabled once balloon gets too low, and is disabled once it gets too high, independent of states. And that finally does conclude our presentation. Thanks for sticking around.